900 million miles away, a planet is losing the only thing that makes it unforgettable, and we're alive at the exact moment it's still visible. Saturn's rings are vanishing. 10 tons of ice fall into the planet every second. In 100 million years, they'll be gone. Here's the paradox: the rings are younger than the dinosaurs. For most of Saturn's history, they didn't exist, and soon they won't again. Why are we living in this brief window? What shattered to create them? Stay with me and subscribe if cosmic coincidences like this keep you curious. Saturn has no ground to stand on. If you tried to land a spacecraft there, you would sink through layers of ammonia clouds, then into hydrogen compressed so tightly it stops behaving like gas and starts acting like liquid, then deeper still into hydrogen, squeezed into a state so extreme it becomes metallic and conducts electricity. Like molten copper churning in total darkness 25,000 kilometers below where the clouds begin. At the core sits a mass of rock and iron 9 to 22 times heavier than Earth, crushed under so much pressure that its temperature climbs to 11,700 degrees Celsius, which is twice as hot as the surface of the Sunday. All of this weight, all of this mass, and somehow Saturn remains light enough to float on water if you could find an ocean large enough to test it. The planet weighs 95 times what Earth weighs, but its density measures only 0.69 grams per cubic centimeter compared to water at 1 gram per cubic centimeter. The reason comes down to composition. Saturn is 96% hydrogen and 3% helium, the two lightest elements in the universe. And even when you crush hydrogen under the weight of an entire planet, atoms refuse to collapse completely, because atoms are mostly empty space. Squeeze them and they push back. Saturn radiates 2.5 times more energy into space than it receives from the Sun, and that extra heat does not come from nuclear fusion, but from helium, rain falling inward through the hydrogen layers, releasing gravitational energy as it sinks. The process has been running for 4 billion years and will continue for billions more. Saturn is a furnace, powered by its own weather. This formless giant somehow generates a magnetic field 580 times stronger than Earth's, though still 20 times weaker than Jupiter's, and the magnetosphere stretches outward to shield the moons and sculpt the particles leaking from the rings. Winds in the upper atmosphere reach 1,800 kilometers per hour, which is 5 times faster than the worst hurricane ever recorded on Earth. And these winds blow in jet streams that circle the equator in bands that have not shifted position in millions of years. The atmosphere stacks into alternating eastward and westward, flows with a precision that looks deliberate, but emerges from physics we still do not fully understand. At the North Pole sits a hexagon-shaped storm 20,000 miles across that has not moved since Voyager spotted it in 1981. 6 perfect sides carved into the chaos. Nobody knows exactly why it forms or why it stays stable decade after decade. But the hexagon and the winds and the metallic hydrogen core are all background to the real story, which is the rings. The rings showed up recently. Not recently by human standards, but recently in cosmic time. Measurements from Cassini, the spacecraft that orbited Saturn for 13 years before NASA deliberately crashed it into the planet in 2017 to avoid contaminating the moons, show that the rings are only 100 to 400 million years old. Saturn itself has been around for 4.5 billion years. For 97% of its existence, Saturn had no rings at all. Earth developed fish forests, reptiles, and then dinosaurs that ruled for 160 million years. And only somewhere during that time did Saturn acquire the feature that now defines it in every photograph and illustration. The leading explanation, supported by computer simulations published in 2023, involves a catastrophic collision between 2 icy moons. Not a gentle bump, but a violent impact that shattered both bodies into fragments and sent debris scattering in all directions. Some of the wreckage fell inward past the Roche limit, which is the distance from Saturn where tidal forces become strong enough to tear objects apart. Inside that boundary, gravity pulls harder on the near side of an object than the far side, and the difference rips it to pieces. The fragments spread into a disk, billions of chunks ranging from dust grains to boulders, the size of houses began orbiting at speeds around 10 kilometers per second, colliding constantly, grinding each other into smaller and smaller pieces. That collision debris is the ring system, not a solid structure but a cloud of fragments held in place by velocity and gravity. 99% of the material is water ice, almost pure, which explains why the rings shine so brightly. Fresh snow reflects sunlight with incredible efficiency, and that is essentially what the rings are: frozen water shattered into a disk. If the rings were ancient, they would have darkened over billions of years as cosmic dust rained down from interstellar space and stained the ice grey or brown. But they have not darkened, they gleam. This brightness is one of the key pieces of evidence that the rings formed recently, rather than alongside Saturn itself during the formation of the solar system. The ring system spans 280,000 kilometers from edge to edge, which is more than twice the distance between Earth and the Moon. But despite that enormous width, the rings measure only 10 to 100 meters thick in most places. If you scaled them down to the size of a sheet of paper, they would be 10,000 times thinner than the paper itself. Vast in one dimension, impossibly thin in another. The particles inside this disk collide endlessly. Some collisions happen gently when two chunks of ice bump and stick together for a moment before separating again. Other collisions occur at 10,000 kilometers per hour, fast enough to vaporize ice on contact and send shockwaves rippling outward through the surrounding material. Embedded within the rings are dozens of small moons that act as shepherds, their gravity carving gaps and sculpting the edges of the disk. Pan orbits inside the Encke gap, a clearing in the A-ring, about 320 kilometers wide, and every time Pan passes through a section of the ring, its gravity pulls particles into waves that trail behind it for thousands of kilometers. The F-ring, which is the outermost bright ring, gets twisted into braids and kinks by the gravity of two small moons named Prometheus and Pandora that flank it on either side. These moons are tiny. Pan measures only 35 kilometers across, smaller than many cities, but the gravitational influence is enough to reshape millions of tons of ring material with every orbit. The rings are not static. They are in constant motion, reshaping themselves over hours and days and centuries, held together by forces balanced so precisely that moving a single moon would destabilize large sections of the system. The main rings have names based on the order they were discovered. The A ring and B ring are the brightest and most massive. Between them sits the Cassini division, a gap 4,700 kilometers wide that looks empty from Earth but actually contains sparse ring material. The gap exists because of an orbital resonance with Mimas, one of Saturn's moons. Every time a particle in the Cassini division completes 2 orbits around Saturn, Mimas completes exactly 1 orbit. The repeated gravitational tugs from Mimas pull particles out of that region over millions of years, sweeping it nearly clean. The B ring contains more mass than all the other rings combined, and in some places becomes so thick with particles that less than 1% of sunlight can pass through. The C ring closer to the planet is translucent and ghostly, visible only because of faint scattered light. Beyond the main rings lie the fainter outer rings. The E ring stretches from the orbit of Mimas all the way out to the orbit of Titan, fed constantly by geysers erupting from the moon Enceladus. The G ring is a narrow band of dust held in place by the gravity of the tiny moon Aegeon. These outer rings are so faint that even spacecraft struggle to photograph them, but they extend the ring system outward for hundreds of thousands of kilometers into space. Consider what this means. Saturn carries a structure twice as wide as the distance to our moon, thinner than anything you could build with human hands, made of billions of independent objects that have been colliding for millions of years without flying apart or collapsing inward. The system balances itself through nothing but gravity and motion. There is no framework holding it together, no central support, just particles obeying the same laws that keep planets in orbit and moons from crashing into their parent bodies. It is fragile in the way that all orbital systems are fragile. Change one variable and the whole thing unravels. And it is unraveling. The rings are not eternal. They are dying as you listen to this. Every second, 10,000 kilograms of material falls from the innermost D ring into Saturn's atmosphere. If you need a way to picture that rate, imagine 10 elephants dropping into Saturn every second. The material gets pulled inward by the planet's magnetic field. Ultraviolet light from the sun charges the ice particles, turning them into ions. Ions follow magnetic field lines. The field lines curve inward toward the planet. The particles spiral downward along those lines and vaporize when they hit the upper atmosphere. This process has been happening for as long as the rings have existed, but it accelerates over time as the rings lose mass and the inner edge creeps closer to the planet. Cassini detected this rain directly during its final orbits, when the spacecraft dove 22 times through the gap between Saturn and its innermost ring, flying faster than any probe had ever flown before. The ion and neutral mass spectrometer sampled the material as it fell, vaporizing the particles on impact and analyzing their chemistry in real time. What the instrument found was surprising. Only 24% of the falling material was water ice. The rest consisted of methane, ammonia, carbon monoxide, butane, propane, silicate dust, and fragments of organic molecules that have not been fully identified. The rings are not as pure as they appear from a distance. They have been contaminated and processed by radiation over millions of years. There is a radiation belt tucked inside the D-ring that was only discovered during Cassini's final months. High-energy protons in this belt strip water molecules apart, breaking them into hydrogen and oxygen, and leaving behind heavier molecules that resist the radiation. This is why the rain falling into Saturn contains so little water. The radiation has already processed it and removed the lighter elements. The rain is not clean ice. It is a chemical slurry, a mixture of everything the rings have accumulated since they formed, now being returned to the planet that created them. At the current rate of loss, the D-ring will vanish in less than 100,000 years. The rest of the ring system will follow over the next 100 million years. That might sound like a long time, but in the context of Saturn's 4.5 billion year existence, it amounts to almost nothing. The rings appeared recently and will disappear soon. You are watching them during the narrow window when they exist. Before this window, Saturn was plane. After this window closes, Saturn will be plane again. The crown is temporary. When the rings are gone, Saturn will resemble the other gas giants in the outer solar system. Uranus and Neptune both have rings, but they are faint, sparse, and completely unremarkable. Jupiter has a thin dust ring that is invisible without special equipment. After Saturn loses its rings, it will look like them. Just another sphere of gas in the outer darkness, nothing to make it stand out, nothing to make anyone look twice. The icon will fade. The beauty will drain away into the atmosphere. Saturn will become forgettable, in the way that most planets are forgettable, defined only by mass and orbit, and chemical composition, no longer the jewel of the solar system, but just another data point in a catalogue of worlds. But that has not happened yet. The rings are still here, still shining, still grinding themselves to dust at speeds that would vaporize anything solid. Cassini measured the total mass of the ring system during its final dives and found that all the rings together weigh about as much as Saturn's moon Mimas. That is it. One small moon's worth of ice spread into a disk wider than the distance to our own moon, thin enough that spacecraft can thread through the gaps without hitting anything. The rings are fragile and temporary and doomed, and yet they define Saturn in ways nothing else does. But the rings are not the only thing Saturn is losing. The planet is consuming itself in another way, one that happens so slowly you would never notice unless you measured it over decades. And the process starts with the same radiation belt that strips water from the falling ring material. Imagine standing under a rainstorm where every drop weighs as much as a car. That is not what is happening at Saturn, but the scale is similar in terms of mass transfer. 10,000 kilograms per second adds up fast. Over the course of a year, Saturn consumes roughly 315 billion kilograms of ring material. Over a million years, that number climbs to 315 trillion kilograms. Over 10 million years, you lose a noticeable fraction of the total ring mass. The rings are not being destroyed by a single catastrophic event. They are being eroded grain by grain, molecule by molecule, in a process so gradual that no human will ever witness a visible change, but so relentless that the outcome is inevitable. The mechanism driving this loss involves forces that operate on scales both vast and invisibly small. Start with ultraviolet light from the Sunday photons, hit water ice molecules in the innermost ring, and knock electrons loose, creating ions. These ions carry an electric charge, and anything with an electric charge responds to magnetic fields. Saturn's magnetic field threads through the space between the planet and the rings, and the field lines act like invisible rails guiding charged particles inward. Once an ion latches onto a field line, it follows that line downward, spiraling along the curvature until it reaches the upper atmosphere. The trip takes hours or days, depending on the starting point, but the destination is always the same. The particle enters the atmosphere at orbital velocity, heats up from friction, and vaporizes in a flash of light too faint to see from Earth. This would be a simple story if the falling material were just water ice, but it is not. Cassini's instruments detected methane, ethane, propane, butane, ammonia, carbon monoxide, molecular nitrogen, and silicate grains in the rain. Some of these molecules are organic, meaning they contain carbon bonded to hydrogen, which makes them interesting to astrobiologists, even though they are not alive and have nothing to do with biology. The presence of organics in the rings suggests that the rings have been collecting material from outside sources, probably micrometeoroids that drift in from the outer solar system and collide with ring particles at high speed. Each impact delivers a tiny amount of non-ice material. Over millions of years, those tiny amounts add up. The radiation belt inside the D-ring complicates the picture further. High-energy protons in this belt move fast enough to break chemical bonds when they collide with molecules. Water molecules are particularly vulnerable because the bond between hydrogen and oxygen is relatively weak compared to bonds in larger organic molecules. When a proton hits a water molecule, it can split the molecule into hydrogen and oxygen. Hydrogen is light and escapes easily. Oxygen is heavier and either recombines into other molecules or gets swept up by the magnetic field and carried away. This process strips water out of the ring material, preferentially leaving behind a higher concentration of everything else. That is why the rain falling into Saturn is only 24% water. The radiation has been processing the material for millions of years, removing the lightest component and concentrating the heavier elements. But the radiation belt itself was only discovered in 2017 during Cassini's final orbits. Before that, scientists assumed the space between Saturn and the rings was mostly empty. It is not. The belt contains protons accelerated to high energies by interactions between Saturn's magnetic field and charged particles leaking from the rings. These protons bounce back and forth between the planet's magnetic poles, forming a stable radiation zone that has probably existed for as long as the rings have existed. Cassini flew through this belt 22 times during the grand finale, and each pass exposed the spacecraft to radiation levels high enough to damage electronics if the mission had lasted much longer. The protons were not evenly distributed. Some regions were intensely radioactive. Other regions were relatively quiet. The belt has structure layers, zones of higher and lower intensity, all shaped by the complex geometry of Saturn's magnetic field and the way that field interacts with the ring system. The rain does not fall evenly across the planet. Most of it concentrates near the equator because that is where the magnetic field lines connect most directly to the D-ring. The material spirals downward and enters the atmosphere in a band that stretches around Saturn's equator like a belt. As the particles vaporize, they release energy in the form of heat and light, but the amounts are so small compared to Saturn's total energy output that the effect is negligible. The atmosphere absorbs the material without noticing. Methane and ammonia mix into the existing clouds. Silicate grains sink deeper into the layers, where temperatures are high enough to melt rock. Water vapor, or what little water vapor makes it through the radiation belt intact, condenses into ice crystals and joins the existing weather systems that churn through Saturn's atmosphere at 1800 kilometers per hour. Consider the timescale involved. The rings are losing 10,000 kilograms per second, which sounds catastrophic until you compare it to the total mass of the rings. Cassini measured the ring system's mass during the grand finale by analyzing how much the rings tugged on the spacecraft as it passed nearby. The measurement required extraordinary precision because but Cassini's instruments were sensitive enough to pick up the tiny deflections in the spacecraft's trajectory, and by combining data from multiple passes, scientists calculated that the entire ring system weighs roughly 4 times 10 to the 19th kilograms. That is a large number, but it is not incomprehensibly large. It is about the same mass as Saturn's moon Mimas, which is 500 kilometers across, and composed mostly of water ice. If you lose 10,000 kilograms per second from a reservoir containing 4 times 10 to the 19th kilograms, the reservoir lasts for about 126 million years before it runs dry. That is the lifetime of the rings at the current erosion rate. But the rate is not constant. As the rings lose mass, they lose the ability to shield themselves from radiation and sunlight. The outer parts of the ring system block some of the ultraviolet light and micrometeoroids that would otherwise hit the inner rings. As the outer rings thin out, the inner rings become more exposed. The erosion accelerates. The D ring, which is already the thinnest and most vulnerable part of the system, will be the first to disappear entirely. After that, the C ring will start to erode faster. Then the Cassini division. Then the A ring and B ring, though those two contain so much mass that they will linger for tens of millions of years after the inner rings are gone. The process is self-reinforcing. Losing mass makes the rings more vulnerable, which increases the rate of loss, which makes them even more vulnerable. There is no equilibrium state where the rings stabilize. The endpoint is always complete disappearance. The only question is how long it takes to get there, and the answer depends on variables we cannot measure precisely. How much mass do the rings contain in regions we cannot observe directly? How fast is the micrometeoroid bombardment rate changing over time? How much material is being replenished by collisions between ring particles that shatter and create new, smaller particles? These questions matter because they shift the timeline by millions of years, but they do not change the conclusion. The rings are temporary. There is something almost tragic about watching a structure this beautiful erase itself. The rings did not ask to exist. They formed because two moons happened to collide in the wrong place at the wrong time, and now they are paying the price for that accident by slowly dissolving into the atmosphere of the planet they orbit. There is no consciousness involved, no suffering, no awareness of loss. The rings are not alive. They are just ice and rock and motion governed by forces that do not care about beauty or permanence. But humans care, and humans are the ones watching this happen with instruments sensitive enough to measure the rate of loss down to the kilogram per second. We are the ones who realize what is being lost. And yet, the loss makes the rings more meaningful, not less. If the rings were eternal, they would be easy to take for granted. They would always be there, unchanging, available to observe whenever we decided to point a telescope in Saturn's direction. But they are not eternal. They are temporary, fragile, and disappearing at a rate we can measure. That makes them precious in a way that eternal things can never be. You cannot lose something that lasts forever, but you can lose something that lasts for 100 million years if you happen to exist during the window when it is vulnerable. The rain continues. 10,000 kilograms per second, 720 million kilograms per day, 263 billion kilograms per year. Every number is exact, measured, confirmed by instruments that flew through the rain and tasted it directly. The rings are not dying in some vague, poetic sense. They are dying in a literal, measurable, scientifically verified sense. And there is nothing anyone can do to stop it because the forces involved are planetary in scale. You cannot turn off Saturn's magnetic field. You cannot block the sun's ultraviolet light. You cannot prevent micrometeoroids from colliding with ring particles. The erosion is built into the structure of the system itself, and it will continue until there is nothing left to erode. But erosion is not the only force reshaping Saturn. At the North Pole, there is a storm that has been running for at least 40 years, and its shape defies every intuitive expectation about how storms are supposed to behave. There is a storm at Saturn's North Pole shaped like a hexagon. Not almost a hexagon or roughly hexagonal. An actual hexagon with 6 sides so straight they look like they were drawn with a ruler. Each side measures 14,500 kilometers long, which makes each edge of the storm wider than the diameter of Earth. The hexagon rotates as a single, rigid structure, completing one full turn every 10 hours, 39 minutes, and 24 seconds, which is the same rate at which Saturn's interior rotates based on measurements of radio emissions from deep inside the planet. The storm has been in this configuration since Voyager 1 photographed it in 1981. It has not drifted. It has not changed shape. It has not dissolved or reorganized. For over 40 years, a planet made of gas and liquid has maintained a geometric pattern that should not exist. Storms on Earth are circular because rotation turns everything into spirals. Hurricanes spin, cyclones spin, tornadoes spin. The Coriolis effect, which arises from Earth's rotation, deflects moving air into curves. You cannot have straight lines in a rotating fluid unless something is forcing the fluid to move in ways it naturally resists. And yet Saturn's hexagon has straight sides. The vertices where the sides meet are sharp, not rounded. The angles are close to 120 degrees. If you drew the hexagon on graph paper and measured the angles with a protractor, you would find that it matches the geometry of a perfect hexagon within the limits of measurement error. The hexagon is not a surface feature. It extends deep into Saturn's atmosphere, possibly thousands of kilometers down into the layers where pressure climbs high enough to compress hydrogen into liquid and then into metallic form. The storm is a jet stream, a river of wind flowing eastward at 320 kilometers per hour, with slower moving air to the north and south. The boundary between the fast jet and the slow air is where the hexagon forms. The 6 sides are the visible manifestation of that boundary, and the straightness comes from the way the jet stream waves interact with vortices embedded in the surrounding flow. Computer simulations run at Harvard University in 2020 offered an explanation that matches the observations. When you simulate a deep convective layer inside a rotating spherical shell, vortices spontaneously form near the poles. These vortices are giant cyclones, powered by heat rising from Saturn's interior. Near the equator, the same convection produces jet streams that flow eastward at different latitudes. Normally, these jets would meander and create wavy boundaries. But if the jet stream interacts with multiple vortices at once, the vortices push on the jet from different directions. Each vortex creates a high-pressure region that deflects the jet outward. When you space the vortices evenly around the pole, they push the jet into a polygon. The number of sides depends on how many vortices fit into the space. 6 vortices produce a hexagon. 4 vortices would produce a square. 8 vortices would produce an octagon. This explanation sounds clean until you try to create a hexagon in a laboratory. Researchers have attempted to reproduce Saturn's hexagon by rotating fluids at different speeds in cylindrical tanks. They have succeeded in creating polygons, but the polygons are unstable. They last for a few rotation periods and then dissolve back into chaos. Saturn's hexagon has lasted for at least 40 years, which is roughly 35,000 rotation periods. Something about Saturn's atmosphere stabilizes the pattern in ways that laboratory fluids cannot replicate. Maybe the stabilization comes from the depth of the atmosphere. Maybe it comes from the temperature gradients that drive convection. Maybe it comes from interactions with Saturn's magnetic field. Nobody knows for certain because the simulations are simplified versions of the real system, and the real system is too complex to model in full detail. The hexagon is not the only feature at Saturn's North Pole. At the center of the hexagon sits another storm, a cyclone roughly 2,000 kilometers across with an eye that looks like the eye of a hurricane. The eye is calm. The wall around the eye contains winds moving at 530 kilometers per hour, which is faster than the jet stream forming the hexagon. This inner cyclone rotates independently of the hexagon. Sometimes it drifts slightly off-center, sometimes it wobbles, but it always stays inside the hexagon, trapped by the structure of the surrounding flow. The hexagon changes color with the seasons. When Cassini arrived at Saturn in 2004, the northern hemisphere was in winter and the hexagon was in shadow. Infrared instruments detected the structure by measuring temperature differences in the atmosphere, but visible light cameras could not photograph it directly because there was no sunlight to illuminate it. In 2009, spring arrived in the northern hemisphere and sunlight began hitting the pole for the first time in 15 years. The hexagon appeared as a bluish-green feature surrounded by golden clouds. Over the next 8 years, as summer approached, the hexagon gradually turned yellow. The color change came from methane in the upper atmosphere, breaking apart under intense sunlight and reassembling into larger hydrocarbon molecules that form a haze layer. The same chemistry creates smog on Earth when sunlight hits pollution in the air. On Saturn, the smog collects inside the hexagon because the jet stream acts as a barrier that prevents the haze from spreading outward. The haze particles inside the hexagon are smaller than the particles outside it. Cassini's instruments measured the size distribution by analyzing how the particles scattered light at different wavelengths. Small particles scatter blue light efficiently and red light poorly, which makes the sky on Earth blue. Large particles scatter all wavelengths equally, which makes clouds white. Inside Saturn's hexagon, the particles are small enough to scatter blue light preferentially, which gives the hexagon a blue tint when viewed in visible light. Outside the hexagon, the particles are larger and scatter all colors equally, which creates the yellow-brown tones visible in most images of Saturn's atmosphere. But the hexagon is not unique in being strange. Saturn's south pole has a storm too, but it is not hexagonal. It is circular, like storms on every other planet. The South Pole storm is also a cyclone with an eye wall and rotating winds, but it lacks the geometric structure of the northern storm. This asymmetry is one of the biggest mysteries in Saturn science. The two poles should be similar. They receive the same amount of sunlight over the course of Saturn's 29-year orbit. They sit at the same latitudes, but in opposite hemispheres. They experience the same Coriolis forces, and yet one pole has a hexagon and the other does not. The difference suggests that something about Saturn's interior is asymmetric, or that the atmospheric conditions at the two poles diverged at some point in the past and have not yet reconverged. One possibility is that the hexagon formed during a specific phase of Saturn's seasonal cycle and became locked into place by feedback loops in the atmosphere. Once the jet stream adopted a hexagonal shape, the shape reinforced itself by organizing the vortices around the pole into positions that maintain the structure. The South Pole might form a hexagon later when conditions shift, or it might never form one at all if the timing is wrong. Observations from the next few decades will help answer this question, but the data required to test the hypothesis will not arrive quickly because Saturn's year lasts 29.5 Earth years and we need to watch through multiple seasons to see if the patterns repeat. The hexagon is larger than Earth. The winds inside it move faster than the fastest winds on Earth. It has persisted longer than human lifetimes, and it formed spontaneously from nothing but heat rotation and the physics of fluid flow. There is no designer, no blueprint, no intention, just a planet with an atmosphere deep enough and hot enough to sustain convection on scales that dwarf anything terrestrial. The hexagon is a reminder that nature can create order without effort, that geometry emerges from chaos when you give chaos enough space and time to organize itself. But the hexagon is not the most violent thing happening in Saturn's atmosphere. Every 30 years, the planet erupts. In December 2010, a white spot appeared in Saturn's northern hemisphere at latitude 37 degrees north. Amateur astronomers noticed it first because professional observatories were pointed elsewhere at the time. Within days, the spot grew large enough to see from Earth with backyard telescopes. Within weeks, it expanded into a storm system 10,000 kilometers across, with a tail that stretched around the planet. Within months, the tail wrapped all the way around Saturn and collided with its own head, creating a turbulent knot of clouds that obscured an entire latitude band. The storm lasted 7 months. Lightning erupted continuously from the core, generating radio bursts strong enough to detect from Earth. At the peak of the eruption, the storm released energy at a rate comparable to a significant fraction of Saturn's total radiated power. This was a great white spot, a phenomenon that appears roughly once every 30 years when Saturn's northern hemisphere tilts toward the Sun and summer arrives. The cycle matches Saturn's orbital period, 29.5 Earth years to complete one orbit around the Sunday. One great white spot per orbit, give or take a few years, depending on when conditions become unstable enough to trigger the eruption. The spots have been recorded 6 times in human history: 1876, 1903, 1933, 1960, 1990, 2010. Each storm followed the same pattern: sudden appearance, rapid expansion, tail formation, planetary encirclement, then gradual dissipation as the energy ran out and the clouds dispersed. The 2010 storm was the first great white spot observed by a spacecraft in orbit around Saturn. Cassini watched the eruption from beginning to end with instruments that could measure temperature, wind speed, chemical composition, lightning frequency, and cloud altitude. The data revealed details that ground-based telescopes could never capture. The storm began as a small bright plume rising from deep in the atmosphere, probably from the water cloud layer, about 200 kilometers below the visible ammonia clouds. The plume punched upward through the overlying layers, carrying water vapor and ammonia into the upper atmosphere, where temperatures were cold enough to freeze both into ice crystals. The crystals reflected sunlight with extreme efficiency, which made the storm appear brilliant white compared to the surrounding clouds. As the plume rose, it encountered wind shear. The upper atmosphere moved faster than the lower atmosphere, so the top of the plume got dragged eastward, while the base stayed anchored near the source. This created the tail. The tail stretched longer with every passing day as the head drifted eastward at 26 kilometers per second, and the base continued pumping material upward. After about 3 months, the tail reached all the way around Saturn and began interacting with the head from the opposite direction. The collision created turbulence that disrupted the organized flow and started breaking the storm apart into smaller vortices. The storm generated lightning at a rate of 10 flashes per second, which is far higher than typical storms on Saturn. Most storms produce a few flashes per second at most. The Great White Spot's lightning was also more powerful. Each flash released as much energy as 10,000 lightning bolts on Earth combined. Cassini detected the lightning using radio receivers that picked up the electromagnetic pulses generated when electrical currents flow through the atmosphere. The pattern of pulses revealed that the lightning originated from deep inside the storm, probably in the water cloud layer, where ice crystals collide and build up electric charge. The charge accumulates until the voltage difference becomes large enough to break down the insulating properties of the surrounding air, and then the current flows as lightning. The storm's energy came from water. Saturn's atmosphere is mostly hydrogen and helium, but it contains trace amounts of water vapor mixed in at various depths. Most of the water sits deep in the atmosphere, where temperatures are warm enough to keep it gaseous. When convection carries this water vapor upward into colder regions, the water condenses into liquid droplets or freezes into ice crystals depending on the temperature. The phase change releases latent heat. Water vapor contains more energy than liquid water, and liquid water contains more energy than ice. When you force the phase change, the excess energy has to go somewhere. It goes into heating the surrounding air, which makes the air less dense, which makes it rise faster, which carries more water vapor upward, which releases more heat, which amplifies the convection. The process is self-reinforcing. Once it starts, it feeds itself until the water supply runs out. The 2010 storm tapped into a reservoir of water vapor that had been accumulating in Saturn's deep atmosphere for decades. After the 1990 Great White Spot dissipated, the water sank back down to lower altitudes and gradually evaporated from the water cloud layer into the overlying hydrogen-helium atmosphere. The water vapor mixed upward through diffusion and convection, but the mixing was slow because Saturn's atmosphere is stably stratified in most places. Warm air stays below, cold air stays above. The temperature gradient suppresses vertical motion. Water vapor can accumulate in this configuration for years or decades without triggering runaway convection because the atmosphere is too stable to overturn easily. But stability is not permanent. Saturn's seasons change as the planet orbits the Sunday. When summer arrives in the northern hemisphere, sunlight heats the upper atmosphere and reduces the temperature difference between the upper and lower layers. The stratification weakens. Convection becomes easier. Eventually, something triggers an instability. Maybe a small updraft in the lower atmosphere punches through the overlying layers. Maybe a density fluctuation creates a pocket of air that is slightly warmer than its surroundings. Whatever the trigger, once convection starts, it does not stop until the water supply is exhausted. The Great White Spot is the result. The 2010 storm affected the entire latitude band from 25 degrees north to 48 degrees north. Winds in the region changed speed and direction. Temperatures in the stratosphere rose by several degrees. Chemical composition shifted as the storm dredged up ammonia and phosphine from deep layers and deposited them in the upper atmosphere where they had never been detected before. The storm also left behind 2 warm spots in the stratosphere that persisted for months after the visible clouds dissipated. These warm spots were anticyclonic vortices, rotating in the opposite direction from cyclones, and they gradually merged into a single large vortex that survived for years. The storm's impact was not confined to Saturn's atmosphere. It affected the rings too. Charged particles from the storm interacted with Saturn's magnetic field and created disturbances in the magnetosphere that propagated outward to the ring system. The disturbances altered the rate at which ring particles became ionized and the rate at which ions followed magnetic field lines into the planet. For a brief period, the ring rain intensified, though the effect was small compared to the long-term average. But the most surprising result from Cassini's observations was the realization that great white spots occur on a schedule. Not a rigid schedule, but a pattern linked to Saturn's orbital period and seasonal cycle. The pattern suggests that Saturn's atmosphere stores energy over decades and releases it all at once when conditions align. The storage mechanism probably involves water vapor diffusing upward from the deep water cloud layer into the overlying hydrogen-helium atmosphere, where it waits for convection to become unstable. The release mechanism involves summer heating that weakens the atmospheric stratification and allows convection to punch through. Once convection starts, it taps into the stored water vapor and releases decades worth of accumulated energy in a matter of months. This is not how storms work on Earth. Earth's storms form and dissipate on timescales of days or weeks. They do not store energy for decades and then erupt all at once. The difference comes from the depth of the atmosphere. Earth's troposphere, where weather happens, is only about 12 kilometers deep. Saturn's troposphere extends down hundreds of kilometers, and the convective layer beneath it goes even deeper. In a shallow atmosphere, convection overturns quickly and prevents energy from accumulating. In a deep atmosphere, convection is suppressed by stable stratification, and energy can build up over long periods before something triggers the release. The next great white spot is expected around 2039 or 2040, give or take a few years. It will probably appear in the northern hemisphere again because the pattern alternates between the equator and mid-latitudes, and the last two storms have been at mid-latitudes. The storm will grow, encircle the planet, generate lightning, release energy, and then fade, just like every great white spot before it. And 30 years after that, another storm will appear. The cycle will continue as long as Saturn has an atmosphere and a seasonal cycle, which means the cycle will continue for billions of years until the sun expands into a red giant and evaporates the atmosphere entirely. But the storms are not the strangest thing orbiting Saturn. Farther out beyond the rings, beyond the radiation belts, there are moons. And two of those moons have features that might make them the most important objects in the solar system for understanding whether life exists anywhere else. Titan is the only moon in the solar system with a thick atmosphere. Stand on its surface, and the air pressure would feel almost like standing on Earth at sea level. 1.5 times Earth's pressure, thick enough to support weather, thick enough to scatter sunlight and create a hazy orange sky, thick enough that if you jumped off a cliff, you would fall slowly because the drag force from the buoyant, dense air would counteract gravity and turn your fall into something closer to a gentle drift. But you would not want to breathe that air. It is 95% nitrogen, which is the same as Earth's atmosphere, but the remaining 5% is methane, not oxygen, methane, an organic molecule that is flammable on Earth but stable on Titan because there is no oxygen to burn it. The surface temperature on Titan hovers around -179 degrees Celsius. At that temperature, water ice is harder than rock, and methane is liquid. Titan has lakes. Not water lakes, methane lakes, ethane lakes, lakes of liquid hydrocarbons sitting in depressions carved into a landscape made of frozen water. The lakes are mostly near the poles, concentrated in the northern hemisphere, where sunlight is weak enough that methane and ethane do not evaporate quickly. Some of the lakes are small, a few kilometers across. Others are larger than the Great Lakes on Earth. The largest, called Kraken Mare, covers an area bigger than the Caspian Sea and contains more liquid hydrocarbons than all of Earth's oil reserves combined. Methane evaporates from these lakes, rises into the atmosphere, condenses into clouds, and falls back as rain. The rain carves channels into the surface, creating rivers that flow downhill and drain into the lakes. The whole system operates like Earth's water cycle, but shifted to a temperature regime where water is solid and methane is liquid. Cassini and the Huygens probe, which landed on Titan in 2005, photographed these features from orbit and from the surface. The images show landscapes that look almost Earth-like: rounded hills, dendritic river channels, coastlines with beaches. But the similarity is superficial. The chemistry is completely different. The rivers carry liquid methane. The rocks are made of water ice. The sand on the beaches is not silicate minerals, but organic compounds created in the atmosphere and deposited on the surface over millions of years. The atmosphere itself is a chemical factory. Sunlight hits methane molecules in the upper atmosphere and breaks them apart into smaller fragments. The fragments recombine into larger molecules: ethane, propane, acetylene, hydrogen cyanide, and hundreds of other organic compounds form in a cascade of reactions that starts with methane and ends with complex molecules large enough to condense into solid particles. These particles create the haze that gives Titan its orange color. They also fall out of the atmosphere and accumulate on the surface, covering the landscape with a layer of organic material that could be meters or tens of meters thick in some places. The James Webb Space Telescope observed Titan in 2022 and 2023 and detected methyl radicals in the atmosphere. Methyl is a fragment of methane with one hydrogen atom removed. It is highly reactive and does not survive long before bonding to other molecules, but its presence proves that methane is actively breaking apart in Titan's atmosphere and fueling the chemistry that creates larger organics. The telescope also observed clouds in the northern hemisphere rising to higher altitudes over the course of several days, which indicates convection. Methane vapor rising from the surface or from lakes heats the surrounding air. The warm air rises, the methane condenses into droplets at higher altitudes, and the condensation releases latent heat that drives more convection. The process is similar to thunderstorm formation on Earth, except the working fluid is methane instead of water. But Titan's methane cycle has a problem. Sunlight breaks methane apart faster than any known process can replenish it. If the only source of methane were the primordial methane that Titan captured when it formed 4.5 billion years ago, the atmosphere would have lost all its methane within 10 million years. Titan still has methane. That means something is replenishing it. The leading candidate is cryovolcanism, which is volcanism where the erupting material is not molten rock but liquid water or water mixed with ammonia. If Titan has a subsurface ocean of liquid water beneath its icy crust, tidal heating from Saturn could keep that ocean from freezing and drive cryovolcanic eruptions that bring methane from the interior to the surface. Cassini found indirect evidence for a subsurface ocean by measuring how Titan's shape changes as it orbits Saturn. The Moon flexes slightly under Saturn's gravity, and the amount of flexing depends on whether the interior is solid or liquid. Titan flexes more than a solid Moon would, which suggests there is liquid inside. The subsurface ocean is probably not pure water. Models suggest it contains ammonia, which lowers the freezing point and keeps the ocean liquid at temperatures that would otherwise freeze pure water. Ammonia is toxic to life as we know it, but it is also a useful solvent for organic chemistry. If you wanted to design a moon where organic molecules could accumulate and interact in liquid form without being destroyed by high temperatures or intense radiation, you might design something like Titan, cold enough that chemistry happens slowly, wet enough that molecules can dissolve and mix, complex enough that a wide variety of molecules are present, protected enough by a thick atmosphere that cosmic rays and solar wind do not strip everything away. Titan is not habitable for humans. The temperature alone would kill you instantly. If you stepped onto the surface without a heated spacesuit, your body would freeze solid within seconds. The methane rain would feel like oil dripping onto your suit. The lakes would look dark and still because there is no wind to create waves in most places. The sky would glow orange from the haze. The sun would be a dim point of light filtered through hundreds of kilometers of smog. You would not be able to see Saturn from the surface because the haze blocks the view. The landscape would look alien in every sense of the word. And yet the processes shaping that landscape would feel familiar. Erosion, deposition, evaporation, precipitation, seasons, weather, all the same mechanisms that shape Earth, just running on different chemistry and different timescales. The question nobody can answer yet is whether Titan has life, not human life or anything resembling terrestrial biology, but some other form of chemistry that meets the definition of life by consuming energy, reproducing, and evolving. Methane-based life is theoretically possible if the chemistry can find ways to build stable structures and catalyze reactions at temperatures where water is frozen solid. The chemistry would be slow. Reactions at -179 degrees Celsius proceed millions of times slower than reactions at room temperature. But slow chemistry is still chemistry, and if you wait long enough, even slow processes can build complexity. Cassini did not find life on Titan. It found methane, ethane, nitrogen, hydrogen, cyanide, and hundreds of other organic molecules. It found lakes and rivers and clouds and rain. It found a moon that looks more like Earth than any other object in the solar system, despite being colder than anywhere humans have ever set foot. The Dragonfly mission, scheduled to launch in 2028 and arrive in the mid-2030s, will land a rotorcraft on Titan's surface and fly between multiple sites to sample the organic material and search for chemical signatures that might indicate biology. Until then, Titan remains a question mark, a frozen world covered in oil and organic sludge, orbiting a gas giant 900 million miles from Earth, possibly harboring the second independent origin of life in the solar system, or possibly just a sterile chemical factory that produces complexity without intention. But Titan is not the only moon orbiting Saturn that might support life. There is another moon much smaller, much closer to the planet, that has an ocean beneath its surface, and that ocean is shooting water into space. Enceladus is 500 kilometers across, which makes it small enough that you could walk around its equator in about 2 weeks if you moved at a steady pace and the surface were flat. It is one of the brightest objects in the solar system because its surface is covered in freshwater ice that reflects 99% of the sunlight that hits it. The temperature at the surface measures -198 degrees Celsius, cold enough that nothing moves, nothing flows, nothing changes except over geological timescales measured in millions of years. And yet, Enceladus is not dead. At the South Pole, there are geysers. The geysers shoot water vapor 500 kilometers into space at supersonic speeds, 200 kilograms per second, which is enough to fill an Olympic swimming pool in a couple of hours. The water does not come from the surface. It comes from an ocean beneath the ice. An ocean 10 kilometers deep, sitting beneath an ice shell, 20 to 30 kilometers thick, kept liquid by tidal heating from Saturn. As Enceladus orbits Saturn, the planet's gravity flexes the moon slightly. The flexing generates friction in the interior. The friction generates heat. The heat melts ice. The melted ice collects into an ocean. Pressure builds. Cracks open in the ice shell at the South Pole. Water escapes. The geysers erupt. Cassini flew through these geysers multiple times between 2005 and 2017. The spacecraft was not designed to sample plumes. Its instruments were built to study Saturn's atmosphere and rings, not the interiors of moons. But the geysers were impossible to ignore. The plume of water vapor and ice particles extended far enough from Enceladus that Cassini passed through it during several flybys, and the instruments recorded everything they encountered. The Cosmic Dust Analyzer captured ice grains and measured their composition. The ion and neutral mass spectrometer sampled gases and identified molecules. The magnetometer detected disturbances in Saturn's magnetic field caused by charged particles in the plume. Every instrument that could measure anything measured something useful. The data revealed that Enceladus's ocean contains more than just water. It contains salt, sodium chloride, ordinary table salt dissolved in the water at concentrations high enough that some of it crystallizes out when the water freezes into ice grains. The presence of salt proves that the ocean is in contact with rock. Pure water ice does not contain salt. Salt comes from minerals dissolving in water, which only happens when liquid water sits on rock for extended periods. This means the bottom of Enceladus's ocean is not ice, it is rock. The moon has a rocky core, overlaid by an ocean, overlaid by an ice shell. Water touches rock, minerals dissolve, chemistry happens. In 2023, scientists analyzing Cassini data announced the detection of phosphorus, in the ice grains. Phosphorus is the last of the 6 elements considered essential for life as we know it: carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. CH-NOPS. Before the phosphorus detection, Enceladus was known to have the first 5, but not the 6th. Phosphorus is rare in the universe and difficult to liberate from rocks because it binds tightly to minerals. On Earth, phosphorus cycles through the biosphere slowly because organisms need it for DNA, RNA, and the energy-carrying molecules that power cellular metabolism. But the supply is limited by how fast rocks weather and release phosphorus into water. Enceladus's ocean has phosphorus concentrations at least 100 times higher than Earth's oceans. The reason comes down to chemistry. Enceladus's rocky core is probably similar in composition to carbonaceous meteorites, which contain carbonate minerals. Carbonates react with phosphate minerals in ways that make phosphorus more soluble. The reaction liberates phosphorus from the rocks and dissolves it into the ocean at concentrations far higher than would be possible in Earth's oceans. The phosphorus detection came from 9 ice grains out of thousands that Cassini sampled. 9 grains showed a clear chemical signature of sodium phosphate salts. The signal was weak but unambiguous. Laboratory experiments confirmed that the signature matches what you would expect from ocean water containing dissolved phosphates that crystallize into salt grains when the water freezes. Geochemical modeling showed that if the ocean is slightly alkaline, which is consistent with carbonates dissolving into the water, then phosphate minerals become much more soluble than they would be in neutral or acidic water. The combination of carbonates' alkalinity and long-term water-rock interaction creates conditions where phosphorus dissolves easily and accumulates in the ocean over millions of years. In December 2023, another team announced the detection of hydrogen cyanide in Enceladus's plume. Hydrogen cyanide is a simple molecule made of hydrogen, carbon, and nitrogen. It is toxic to humans, but it is also one of the key building blocks for creating amino acids and nucleotide bases, which are the components of proteins and genetic material. The presence of hydrogen cyanide suggests that Enceladus's ocean contains not just the elements needed for life, but also some of the chemical precursors that could assemble into more complex molecules. The ocean is not warm everywhere. Most of it is probably near the freezing point of water, which is 0 degrees Celsius at Earth's surface pressure, but slightly lower under the pressure of the overlying ice shell. However, if the rocky core is hot enough, there could be hydrothermal vents at the bottom of the ocean, where water heated by the core rises and mixes with the cold ocean water. On Earth, hydrothermal vents support ecosystems that do not rely on sunlight. Instead, they rely on chemical energy from reactions between hot water and minerals. Bacteria near the vents oxidize hydrogen sulfide and other reduced compounds to extract energy. Larger organisms eat the bacteria. The whole food chain is powered by geochemistry instead of photosynthesis. If Enceladus has hydrothermal vents, and if there is life in the ocean, it would probably cluster near the vents where energy is most available. Cassini detected molecular hydrogen in the plume, which is indirect evidence for hydrothermal activity. Molecular hydrogen forms when hot water reacts with certain types of rock, particularly rocks containing iron and magnesium silicates. The reaction, called serpentinization, oxidizes the iron in the rock and reduces the water-producing hydrogen gas as a byproduct. On Earth, serpentinization reactions happen at hydrothermal vents and provide energy for microbial ecosystems. The detection of hydrogen in Enceladus's plume suggests that similar reactions are happening at the bottom of the ocean, which means the ocean has an energy source independent of sunlight. But detecting these molecules does not prove that life exists. It proves that the ingredients and energy sources needed for life are present. Whether those ingredients have assembled into something that meets the definition of life is a question that cannot be answered from orbit. You would need to go to Enceladus land, on the surface near the South Pole, drill through the ice and sample the ocean directly. Or you would need to fly a spacecraft through the plume with instruments sensitive enough to detect biological molecules like amino acids, lipids, or ATP. Or you would need to land near one of the geysers and collect ice grains over a long period, then analyze them in detail to look for patterns that only biology can create. NASA and the European Space Agency have discussed missions to Enceladus, but none have been approved yet. The technical challenges are significant. Enceladus is 900 million miles from Earth. Getting there takes years. Landing on a low-gravity moon covered in ice requires precision. Drilling through ice requires power and equipment that might not survive the radiation environment near Saturn. Sampling the plume is easier, but even that requires instruments more sensitive than what Cassini carried, because you need to distinguish biological molecules from the organic molecules that form naturally in space. The geysers are not constant. They vary in intensity depending on where Enceladus is in its orbit. When the moon is farthest from Saturn, tidal stress is lower, the cracks in the ice open wider, and the geysers spray more material into space. When the moon is closest to Saturn, tidal stress is higher, the cracks squeeze shut slightly, and the geysers weaken. The variation is measurable. Cassini detected it by flying through the plume at different points in Enceladus's orbit and counting how many ice grains hit the spacecraft per second. The data showed a clear pattern linked to orbital position. This pattern confirms that the geysers are powered by tidal flexing, and not by some other energy source, like internal radioactive decay. Enceladus has been geologically active for a relatively short time compared to its age. The surface near the South Pole is young, with few craters, which means it has been resurfaced recently by fresh ice erupting from the interior. The rest of the moon is older, covered in craters heavily scarred by impacts that happened billions of years ago. The contrast suggests that the South Pole became active within the last 100 million years or so, possibly triggered by a resonance with another moon that increased tidal heating. Before that, Enceladus was probably frozen solid with no ocean and no geysers. After the geysers stop, which they will eventually, when tidal heating declines, the ocean will freeze and the surface will become inactive again. We are seeing Enceladus during the brief window when it has liquid water and active geology. But we are also seeing it during the window when humans have the technology to detect those features. Voyager flew past Enceladus in the 1980s and saw a bright, icy moon with a strange, smooth region near the South Pole. Voyager's instruments were not sensitive enough to detect the geysers. Cassini arrived in 2004 with better instruments and saw the geysers immediately. If Cassini had arrived 100 million years earlier, the geysers might not have existed. If it arrives 100 million years later, they might have stopped. The timing is almost too convenient. We developed the ability to explore the outer solar system at almost exactly the moment when one of Saturn's moons became interesting enough to justify the effort. And the effort to understand Enceladus is not done. The data from Cassini will be analyzed for decades. Models will improve. Simulations will become more sophisticated. New missions will be proposed, and some will be approved. Eventually, a spacecraft will return to Enceladus with instruments designed specifically to search for life, and that mission will either find something or rule out the most obvious possibilities. Until then, Enceladus remains a tantalizing possibility. A small, frozen moon with an ocean that contains everything life needs and no clear reason why life should not exist there. But the story of Enceladus would be unknown if not for a spacecraft that spent 13 years orbiting Saturn and then destroyed itself to protect the very moons it discovered. Cassini launched from Earth in October 1997. It carried the Huygens probe built by the European Space Agency, which would eventually land on Titan. The journey to Saturn took 7 years. Cassini flew past Venus twice, Earth once, and Jupiter once, using gravitational assists to gain speed and adjust its trajectory. It arrived at Saturn in June 2004 and fired its main engine for 96 minutes to slow down enough to enter orbit. The engine burn worked. Cassini became the first spacecraft to orbit Saturn. For the next 13 years, Cassini orbited Saturn and studied the planet, the rings, and the moons. It completed 294 orbits. It flew past Titan 127 times and past Enceladus 23 times. It photographed the hexagon at the North Pole and the storms at the equator. It measured the ring's mass and detected the ring rain. It discovered new moons and observed seasonal changes in Titan's atmosphere. It sampled the plumes from Enceladus and found salt organic molecules and eventually phosphorus and hydrogen cyanide. It took 450,000 images and collected 635 gigabytes of data. Every observation answered questions and raised new ones. Every flyby revealed details that had been invisible from Earth. But Cassini was not designed to last forever. It carried a finite amount of fuel. The fuel powered the thrusters that adjusted the spacecraft's trajectory and kept the antenna pointed toward Earth. Without fuel, Cassini would lose the ability to control its orientation. The antenna would drift. Communication would fail. The spacecraft would become a piece of space junk drifting through the Saturn system on an uncontrolled trajectory. Eventually, it would crash into something. Maybe one of the rings, maybe one of the moons, maybe Saturn itself. NASA did not want Cassini to crash into Titan or Enceladus. Both moons have environments that might support life. Titan has organic chemistry and liquid methane. Enceladus has a subsurface ocean with all the ingredients life needs. If Cassini crashed into either moon, it might contaminate them with bacteria from Earth. The spacecraft was assembled in clean rooms, but clean rooms are not perfectly sterile. Microbes can survive in extreme environments. Some bacteria form spores that can withstand vacuum radiation and temperature extremes. If even a few bacteria survived on Cassini's exterior and made it to the surface of Titan or Enceladus, they could potentially survive long enough to contaminate the environment and compromise future searches for native life. Planetary protection protocols exist to prevent this kind of contamination. The protocols are international agreements enforced by the Committee on Space Research, which operates under the authority of the United Nations Outer Space Treaty. The protocols classify solar system bodies based on their potential for hosting life or conditions suitable for life. Enceladus and Titan are both classified as high-priority targets for planetary protection because they have liquid water or organic solvents and energy sources. Any mission that might contact these bodies must be sterilized or disposed of in ways that prevent contamination. Cassini was not sterilized. Sterilization was not technically feasible in the 1990s when the spacecraft was being built. The electronics and instruments could not survive the high temperatures required to kill all microbes. NASA's solution was to dispose of Cassini before it ran out of fuel. The plan was called the Grand Finale. In late 2016, Cassini began a series of orbits that passed just outside the F ring, the outermost bright ring. These were the ring-grazing orbits, 20 orbits each one, bringing the spacecraft closer to the rings and allowing high-resolution observations of the ring structure and the small moons embedded within the rings. The ring-grazing orbits were a warm-up for the final phase. On April 22, 2017, Cassini flew past Titan one last time. The gravity assist from Titan bent Cassini's trajectory and sent it on a path that would dive between Saturn and the innermost ring. This was unprecedented. No spacecraft had ever flown through the gap before. Nobody knew what was in the gap. Models predicted mostly empty space with a few dust particles, but models are not always right. If the gap contained more material than expected, the particles could damage the spacecraft or knock it off course. Cassini would be flying at 77,000 miles per hour. A dust grain, the size of a sand particle hitting at that speed, would release as much energy as a small explosive. The first dive happened on April 26th. Cassini oriented itself so the antenna pointed forward, acting as a shield to protect the instruments from dust impacts. The spacecraft passed within 3,000 kilometers of Saturn's cloud tops and 300 kilometers from the inner edge of the D ring. The dive lasted several hours. For most of that time, Cassini was out of contact with Earth because the antenna was pointed in the wrong direction. When the spacecraft emerged from the dive and reoriented to point the antenna toward Earth, it transmitted the data it had collected. The gap was not empty, but it was not as hazardous as feared. The dust density was low enough that Cassini survived without damage. Over the next 5 months, Cassini completed 21 more dives. Each dive brought the spacecraft slightly closer to Saturn. Each dive collected data on the rings, the magnetic field, the gravity field, and the atmosphere. The data revealed the ring rain falling into the planet. It revealed the radiation belt inside the D ring. It revealed fine structure in the magnetic field that suggested the field originates deep inside Saturn rather than in the outer layers. It revealed that Saturn's interior rotates at a rate slightly different from what the cloud patterns suggested. Every dive answered questions that could not be answered from farther away. On September 15, 2017, Cassini made its final dive. This time, the spacecraft did not pull up. it continued descending into Saturn's atmosphere. The atmospheric drag increased. The thrusters fired continuously to keep the antenna pointed toward Earth, but the drag grew stronger than the thrusters could counteract. The spacecraft began to tumble. The signal weakened. At 11:55:46 UTC, Earth's Deep Space Network lost contact with Cassini. The signal did not return. 30 seconds later, traveling at 126,000 kilometers per hour, Cassini broke apart from aerodynamic forces and vaporized in Saturn's upper atmosphere. The atoms that once made up the spacecraft are now part of Saturn's clouds, mixed into the hydrogen and helium indistinguishable from the planet itself. The decision to destroy Cassini was deliberate. NASA had other options. The spacecraft could have been parked in a distant orbit where it would not interfere with anything. It could have been sent on a trajectory that would eventually take it out of the Saturn system entirely, but both options carried risks. A distant orbit might decay over decades or centuries, and eventually bring Cassini back into the inner system where it could collide with a moon. An escape trajectory might fail if the navigation was not precise enough, and the spacecraft could end up on a collision course with Titan or Enceladus years or decades later when nobody was monitoring it. The only option that guaranteed no contamination was to destroy the spacecraft in a controlled manner while it still had enough fuel to execute the maneuver. The destruction was also scientifically valuable. The final dive collected data on Saturn's atmosphere that could not be obtained any other way. The instruments sampled gases at different altitudes as the spacecraft descended. The radio signal provided information on atmospheric density and temperature. The magnetometer measured the magnetic field deep inside the magnetosphere. The gravity measurements refined models of Saturn's interior structure. Even the loss of signal carried information, because the timing of the signal loss revealed how quickly the atmosphere became dense enough to disable the spacecraft. Cassini's mission produced 635 gigabytes of data and more than 4,000 scientific papers. It discovered 7 new moons. It confirmed that Titan has a methane cycle and a subsurface ocean. It revealed that Enceladus has geysers and an ocean that might support life. It detected the ring rain and measured the rate at which Saturn is losing its rings. It observed seasonal changes in the atmosphere and tracked storms that lasted for months. It photographed Saturn and its moons from angles and distances that no ground-based telescope could ever achieve. Every measurement expanded our understanding of the Saturn system and raised new questions that future missions will attempt to answer. But Cassini also demonstrated something more fundamental. It showed that humans can build machines capable of traveling nearly 1 billion miles from Earth, surviving in a radiation-filled environment for 13 years, and executing complex maneuvers with precision measured in kilometers even. When light takes over an hour to travel between the competi, spacecraft, and the control room. It showed that we can study worlds so different from Earth that even the basic rules of what counts as weather or geology have to be rewritten. It showed that curiosity is powerful enough to justify spending billions of dollars and decades of effort to visit a planet that humans will probably never set foot on. And it showed that responsibility matters. Cassini was destroyed to protect the moons it discovered. The spacecraft that revealed Enceladus's ocean and Titan's methane lakes could have contaminated those worlds if it had been allowed to crash into them uncontrolled. The decision to prevent that contamination, even at the cost of losing the spacecraft while it was still functional, reflects a commitment to preserving the integrity of the environments we study. We do not own the solar system. We are visitors, and visitors who care about what they are visiting do not leave trash behind or introduce hazards that future visitors will have to deal with. Cassini is gone. The data remains. The questions remain. And Saturn remains orbiting the Sun as it has for 4.5 billion years, indifferent to whether humans are watching or not. Saturn will not always look like this. In 100 million years, the rings will be gone. The rain falling into the atmosphere will strip away the D ring first, then the C ring, then the Cassini division, then the A and B rings. The F ring, which is already faint, will vanish even sooner. The shepherd moons will remain orbiting through empty space, where the rings used to be, and eventually their orbits will decay and they will crash into Saturn or migrate outward beyond the point where they have any influence on anything. The outer moons will stay where they are because they are far enough from the planet that orbital decay takes billions of years instead of millions. But the rings will be gone. After that, Saturn will look like Neptune, like Uranus. A bland gas giant with maybe a thin dust ring left over from micrometeoroid impacts on the remaining moons, but nothing bright, nothing visible from Earth with a small telescope, nothing that would make anyone describe Saturn as beautiful. The hexagon will still be there, spinning at the North Pole, because the hexagon does not depend on the rings. The great white spots will still erupt every 30 years because those storms are driven by seasonal heating and water vapor in the atmosphere. Titan will still have methane lakes and rain. Enceladus will still have geysers at least for a while until tidal heating declines and the ocean freezes. But the one feature that makes Saturn instantly recognizable, the one thing that has defined the planet in human imagination since Galileo first pointed a telescope at it, will be gone. This is not a hypothetical future. It is a measurable prediction based on the current rate of ring loss, 10,000 kilograms per second, 263 billion kilograms per year. Over 100 million years, that adds up to 2.6 times 10 to the 19th kilograms, which is close to the total mass of the rings. The math is simple, the physics is simple, the outcome is inevitable unless something disrupts the process, and nothing is going to disrupt the process because the forces involved are too large for anything short of a major collision to affect. The rings appeared recently. Something violent happened. Two moons collided. The debris scattered. Some of it fell inside the Roche limit and spread into a disk. The disk has been eroding ever since. We are alive during the middle of the erosion process, after the rings became visible, but before they vanish completely. The timing is pure chance. Humans evolved on Earth, developed technology, built telescopes, sent spacecraft to the outer solar system, all during the brief window when Saturn has rings. If humans had evolved 1 billion years earlier, Saturn would have been plain. If humans evolve 1 billion years later, assuming humans still exist in any form recognizable as human, Saturn will be plain again. But we are here now, and Saturn is not plain now. The rings are still bright. The geysers on Enceladus are still spraying water into space. The methane lakes on Titan are still liquid. The hexagon is still spinning. The great white spots are still erupting every 30 years. All of these features are temporary on geological timescales, but geological timescales are so long that they might as well be eternal from a human perspective. 100 million years is longer than humans have existed as a species, longer than mammals have been the dominant form of land life on Earth, longer than the breakup of Pangaea, longer than most mountain ranges survive before erosion wears them flat. On human timescales, 100 million years is forever, but on planetary timescales it is nothing. Consider what this means. Saturn has existed for 4.5 billion years. The rings have existed for maybe 400 million years at most. That is less than 9% of Saturn's lifetime. For more than 90% of its existence, Saturn was plain. It had moons, it had storms, it had a magnetic field and an atmosphere and all the features that define a gas giant. But it did not have rings. Then, in a moment of violence that lasted seconds or minutes, two moons collided and created the debris that would become the most recognizable feature in the solar system. The rings have been visible for a few 100 million years. They will be visible for another 100 million years. Then they will be gone, and Saturn will return to being plain for the remaining 4 billion years of its life before the sun expands into a red giant and destroys everything in the inner solar system. You are alive during the narrow window. Not by design, not because the universe arranged things to accommodate your existence, by pure chance. The universe does not care whether you exist or not. It does not care whether Saturn has rings or not. It does not care whether Enceladus has an ocean or whether Titan has methane lakes. The universe operates according to physical laws that produce outcomes without regard for beauty or meaning or significance. Gravity pulls, particles collide, energy dissipates, entropy increases. Stars form and die. Planets form and change. Moons collide and create rings. Rings erode and disappear. None of it means anything unless someone is watching and decides that it means something. Humans are watching. Humans have decided that Saturn's rings are beautiful. That decision is subjective, arbitrary, and completely valid. Beauty is not a property of the rings themselves. It is a property of the interaction between the rings and the human brain, which has evolved to recognize patterns and assign emotional significance to things that trigger specific responses in the visual cortex. The rings trigger those responses. They are symmetrical, they are bright, they have structure. They look like something that should not exist but does exist, and that contradiction creates a sense of wonder that translates into the experience of beauty. But the experience of beauty does not change the physics. The rings are still eroding, 10,000 kilograms per second. The rate does not slow down because humans find the rings beautiful. The universe does not adjust its behavior based on human preferences. The rings will disappear on schedule regardless of whether anyone is watching or whether anyone cares. And after they disappear, the universe will continue operating exactly as it did before, indifferent to the loss, indifferent to the fact that something beautiful once existed and now does not. This is not a sad fact, it is just a fact. Temporary things are not less valuable because they are temporary. If anything, the temporariness makes them more valuable because it creates scarcity. Things that last forever are easy to take for granted. Things that exist for a limited time demand attention because you know the opportunity to experience them will not last. Saturn's rings are scarce, not in the sense that they are rare in the universe, though they might be, but in the sense that they exist for a limited time and we happen to be alive during that time. The scarcity is what makes them worth paying attention to, and paying attention is what humans do. We build telescopes, we send spacecraft, we analyze data, we write papers and take photographs and create simulations and argue about interpretations and revise models and propose new missions. All of this effort is driven by curiosity, which is the impulse to understand things that we do not already understand. Curiosity does not require the universe to be designed for us. It does not require meaning to be built into the structure of reality. It only requires that we notice things and want to know more about them. We noticed Saturn's rings. We wanted to know more. We built Cassini. Cassini told us more. Now we know more, and we want to know even more. So we propose new missions and new instruments and new ways of asking questions that have not been answered yet. The rings are dying. Enceladus is shooting water into space. Titan is raining methane. The hexagon is spinning. The great white spots erupt every 30 years. All of this is happening whether we watch or not, but we are watching, and the act of watching is what transforms indifferent physical processes into stories that matter. Saturn does not care that it has rings. Humans care. That difference is everything. The rings are beautiful because we are here to see them, and because we have decided that beauty is a thing worth recognizing. Because beauty that vanishes is beauty that cannot be taken for granted. Saturn is 900 million miles away. The rings are eroding. The geysers are spraying. The storms are churning. And somewhere in all of that distance and motion and chemistry, there is a reminder that the universe produces things worth seeing. Even if those things are temporary, even if they exist for no reason other than that the laws of physics allowed them to form. The rings are not eternal, neither are you. But both of you are here now at the same moment, and that is enough.